everybody, your favorite artist electronics Mr. Q12 here with a new and interesting project and subject. It's about this. This is the folder, LED chaser and a scanner with 4017, and I have a little bit of story about it. What I'm interested to show you is the circuits, basically all the circuits that I built. I was helped by some people in some critical moments when I didn't knew how to start first of all and then on the road, but mostly I did my part as well. I'm building them myself and I put my mind to it to make them as convenient as I could think of. But at the end of the road, I couldn't actually find a reason to use them, an end usage. So basically, this is, it will be more like a toy. This kind of circuit is more like a toy. But first of all, it was a very, very interesting and good experiment and lesson for myself, for my brain. So I learned quite a bit about flip-flops, how to use them, about this specific chip, which is a counter 4017, and you will see, and also transistors as well, and some AND gates, because I have a tiny little bit of story. I hope I will not forget it. Let me start first like this. This is the name of the folder, all right? So inside this folder, I'm having all these projects, and these projects are made in Proteus 8. You can see it here in my desktop. I'm making a picture of the circuit diagram. You can see it here. I can scroll very quickly between the circuits and find what I'm looking for when times comes, you know, to find something in my circuit. So this is a very good mentality to have the circuit picture next to your project. You know, and here it is. This is the first circuit. Now, let me actually show you the basic. This is from internet. This is a picture from internet. I don't have it in my simulator here. So this everything started with this circuit diagram. What we are having here, the first half of the circuit is is a clock. This is a clock here. It's clocking this pin 14. This is its entire purpose. And this 4017 counter is being clocked through this pin here, and as long as it is clocked, it is counting all its outputs, and then is resetting back to 0. When it's reaching this 9, output 9 is resetting to 0. So this is a very elementary, a very cute, very nice, very practical counting circuit, and I really love it. So let me go to 4017. So electronic MIC, and here basic circuits. This is the basic circuits on 4017. I have it here. Okay. So this is the, like the name says, basic. It's the basic circuitry that you can use this chip, and I'm adding to it. I'm adding to this file, and I can look back here and remember how to link everything, where every pin, setting pin needs to be connected, etc., etc. So this is how it started. These two here are the basic, how to link the chip, and then the next circuit I was having this one, which is a cascading. When A chip here is clocking a B chip here through this line, clocks out, is not doing it sequentially one after one. What I mean is after Q9 to go to Q0, then continuing Q1, 2, 3 to 9 here, and then come back to here. So it's not doing it like one by one, but it's doing it binarily, meaning when A chip is finishing its pass up to Q9 here, and when it's resetting to Q0, it's transmitting that switching to this B chip here, and is incrementing it with a 1. And then I will start another round. Let me actually exemplify it. So look here on this red outputs when it's becoming red, and here is incrementing when this is finishing one pass. Is incrementing by one pack and pack and pack and back to 0, and so on. So it needs 10 passes for this, and when it's reaching the 10th pass, the 10th step is incrementing with 1. And that's it. It's very, very basic. But I didn't like it. I mean, it's very good for to build a clock like this. These are the minutes, and these are the seconds here, or whatever. But in this configuration, exactly in this configuration, I use it as a clock, and it's very good to use it like this. But what I wanted actually was to do a sequential one after another, and not repeat this and increment this with 1 after it's finishing first. But when it's finishing this, to switch to this one and number Q0 to Q9 here, and when it's finishing this, these two will be off, and this will come on, and will start from 0 to 9. And then when this is finishing here, shut off and start again. So these two will remain off, and only this chip is on and counting its pass. So that was the idea. So incremental cascading. Okay, so this was a very, very interesting idea I had, and everything started from this basic file that I'm having here, that I'm presenting here. That's the reason why I really wanted this functionality to have it. Okay, let's get back to our folder here. Let me actually show you. So this is the title, how to make a 20 LED chaser with 47. So I was thinking how to make it easy to begin with, and then easy to continue it, to extend it. You see here, this is the main problem, how to make a 20 LED chaser with 4017, but only one LED at a time and counting from 0 to 20. And this guy is saying, yes, good question, after he actually understood what I'm after. And this guy comes in and says, well, he find this circuit in the datasheet. And okay, and I go to my datasheet. Brand, Nexperia brand, another Texas Instruments here for some reason, I don't know. But some are worse than other, and only one or two are good. Is the good stuff. This is the closest. I couldn't find his diagram that he's having here. I actually asked him where his datasheet is from, and he didn't answer me. But I find this one here. But what I was having before all this, how many I have? 1, 2, 3, 4, 5, I have 6. And before I was having only 3. In only one, I was having this circuit, but 2 of them were missing this circuit inside. So be careful with the datasheets that you collect from internet, because some are they are literally cutting out a lot of good stuff from the datasheet just because they are meant to be for the general public and not for the army, where in the army they need every example, every possible example, every detail, but the general public doesn't need to know everything. So that's the reason you will find cut off datasheets like this. This is the reason. This is the only reason I can think of. I'm not sure if it's the real reason, but who knows. So let's see. Let me zoom it out like this to be easy to scroll down. And as you can see, nothing here. No sample circuit timing diagrams. This is the internal, how it's looking internally and how it's doing the timing, but not a sample circuit. So it's definitely a cut out datasheet specifically for the general public, not for the army, and or for the science department, or the real deal. I had another one, pretty basic, like this one. What other sample circuits do you need? If you have the pins, it's good for you, And so then I searched further on the internet. I searched deeper, and I started to get everything that I could put my hands on, in the hope that I can find this specific datasheet, the screenshot that is this guy is showing here. And I couldn't find it at all. And it's looking like it's an old version, but my version that I'm having here is a bit newer than his, and it's pretty much the same thing. And if I had it before, I totally overlook it. I didn't figure it out from the first look what this shit means. And when I started this project, I was looking in the datasheets that I had, but very, very, very fast. And I totally overlooked this circuit, what it was doing there. But this guy came with the exact same thing and is showing it here. And I said, well, let me test it. This is the one. I extended it here. Why don't I have this? What the fuck? Version patrol. Export. Here you can see how I'm making this pictures. So I'm doing that. And I'm getting this EMF file, which I'm converting it to JPEG and save it, and that's it. On this EMF, I'm deleting it if I don't need it. And I'm getting this. I didn't have this this specific important picture. Let me cut out this like this and save it or write it. All right. So yeah, I didn't have the picture, the image for my project that I'm having here. So it's exactly like that. You see it side by side like that. You see? Exactly. Okay. So I built it, and it worked absolutely fine. It worked perfect. Actually, I can show it, and you can see is turning off the others and is letting one moving on only. So it's functioning only one chip at a time, pretty much. And you can see here some numbers, 9, 8, 8, which they represent the number of the output, the number of LEDs on these outputs. And here on the first, I'm having 9 that are operational. But here on the rest, I'm having only 8, and until the last one. So 9 plus 8 plus 8 equal 25 in total. So instead of 30, because there are 10 outputs per chip, so 3 chips times 10 equal 30. Instead of 30 LEDs, or 30 output, usable outputs, I'm only getting 25. So it's a little bit, I don't like it personally. But because it's cutting off some outputs, you cannot use them. Why you cannot use them? Because it's using a trick. Let me actually link this to here. When this is not, the chip is not actually cut off, the power of it is not cut off, but it's resetting to this first line that is having here. And when I'm doing this, you see it's counting, but this is remaining stuck on the first until it's activated. And on the last pin here, the Q9, it needs to talk with other chips. And the same for this one is talking with this gate. Here is talking again with this gate, but in this case, it's talking to the first chip back. And that's why you need the first and the last pins, output pins, for basically for logic communication. But the in between from pin 2 to pin 9, actual usable outputs you get from this entire chip. So that's a little bit of problem. I didn't like it. To be sincere, I didn't like it, but it is functional. It is a very functional circuit. So this was the first circuit that I got working one by one, And this is it. This is the exact same thing. Here it is. This is I screenshotted this circuit that I'm having here, and this is a screenshot of that. And I posted it, and I said, well, it's working excellent. Thank you. It works. You see here. And I was very pleased. But after that, after this circuit, I said, well, I want more. I want more outputs or more LEDs, just as a training, just as an exercise. You know, I'm not really thinking to build anything, but if I will, most probably I will build it on breadboard just to see it working in reality a little bit. But most probably I will not make it standalone by its own board. You know, just on breadboard for testing purposes, and that's it. All right. So next I build this one, which is again functioning absolutely fine. There's no problem. And again, I'm having, let me stop it. I'm having this 9888 LEDs, usable outputs, and in total is 33 instead of 40. So I'm having 4 chips with 10 outputs equals 40 outputs. But here I'm getting way less than I wished. But again, it's a functional circuit and it's very usable. And this is from the Texas Instruments datasheet. Not this one, actually, this one. Okay, let me close this. Save no, because I didn't do anything to that. Okay, next. And then this guy, Johnny1230, give me his Proteus circuit to try it. And I don't have its original. It's looking a little bit different than mine, but my circuit is a little bit more clean up. And this is, I believe, this is it. Yeah, from Johnny. Okay. So you see how quickly I can find what I'm searching for by opening only the picture and closing it. And then I'm going to the project file and I'm opening because I know exactly that this is what I am looking. I'm looking outside of the circuit to see if I'm having something else outside of the board. But this was his circuit, and what he is having here is a very, very, very clever thing. Very clever. I really like it. I really like it. And this is the winner. Is even better than the Texas Instruments circuit example, in my opinion. This is a bit better than that. When I'm playing it, you can see, and I will explain very quickly why it's better. From pin 1 here, from this pin 3 actually, output 0 here, is this link, which is 1, numbered 1, 2, 3 to 10. You see, and this link, let me actually draw it for you, is linked to this here. And this pin 2 is linked to this, and so on and so forth. I will on the back. So this little circles and the numbers next to it, they are shortcuts, pretty much, not to make too many lines. You know, to drag too many lines to each LED, because it's this is a diagram. It's only an exemplification what you really need to do it in reality. So that's what these strange notations I'm having here. And as you can see, is repeating again for this other set. So I'm having 2 sets of LEDs, 10 LEDs here and other 10 LEDs there. But why this is better than that official Texas Instruments circuit is because it is using, as you might already observed, all the 10 LEDs, all the 10 outputs of the chip. And this is net superior. I give it a 10 in my book. I really like it. And it is using a flip-flop here, 4013 or whatever flip-flop you want. In my case, I believe his original circuit was using a 4013, but I don't have a 4013 in my list of flip-flops of chips. Let me actually check it very quickly. So like this here. So my IC list. Let me search a little bit. It should have been here 4013 here on this line before, but I don't have that chip. I know for sure I don't have it. But I've seen it in many other circuits. But I have other flip-flops. I'm having this 4027. This is a JK, and if I remember right, 4013 is a DTFF. It means D-type flip-flop. And if I'm searching for another D-type flip-flop, you see, I'm having this 7474, and I have 70 of them. When I buy 20 of them, but I remained right now. I used only 3. I'm not updating every time this list. Unfortunately, I am updating it, but very rarely. So all these data are less or more accurate, the ones that I remained with. So I can use this 7474, specifically D-type flip-flop, but I can use a JK flip-flop as well if I'm having too many, or if I want to get rid of 1 or 2 that I just don't want them anymore. You know, so that's the flip-flop is using, and here is a MOSFET that you can use a NPN as well. Doesn't matter. And this is a very, very clever. I was looking on his circuit originally, and I was thinking, why doesn't have this MOSFET doesn't have a resistor to ground here linked? Because this is a N channel MOSFET, and usually it must have a resistor linked to the ground here, 10 kilo resistor or something like that, and it's only having 1 single base resistor for limiting the current. But then I realized, after playing with the circuit a little bit, then I realized that the flip-flop is non-inverted, and this is inverted output, you know, and then this first output is linked to this, and this not inverted output is linked to this. So this output, this specific output is 0 volts, then 5 volts, low, high, low, high. So this is practically is bringing down and shutting off. When it's low, when it's 0 volts, is shutting off the MOSFET, and when it's high, is activating the MOSFET and is letting the current pass through the MOSFET, and all this. So it's enabling or disabling the MOSFET pretty much from only one pin, one flopped pin, you know, when it's needed. And this is clocked when this chip is the end of one cycle. It's very, very clever circuit diagram. I never seen something like this before. That's why probably this is the main reason that I'm making this video, to praise this guy from Poland, that he did a very, very good. I really like it. I really like it. Very good circuit, and I like it from the first look on it. You know, All right, let me show it another time here. This is the frequency. It's random. You can put your own frequency that you want. You can put a button. You can put a frequency generator, whatever you want here on this clock pin with a 555 or whatever. It doesn't matter. That's up to you to find a clocking circuit to link it to that clock pin, or a button, or a wire. You want, if you want, you can use a wire and tremble it or move it, and creating a small input pulses like that with your finger. You can do whatever you want. All right. Or you can bring, or you can leave this clock pin floating, and if you bring your hand and put a single wire, but not linked to any kind of rail, just like an antenna, and if you get your hand closer to that wire, that antenna linked to this clock, it will work. It will clock quite precisely, I may add, at exactly 50 hertz. That your body is an antenna, and it is receiving 50 hertz from the mains that you have around you, especially if you are in a block like I am, and not in a house in the middle of the field, but here in the city where the 50 hertz is all around us, and we are catching that 50 hertz, and you can use that 50 hertz and with an antenna linked to that clock, and you can use that shit also, just for fun. Again, this is more like a toy circuit for me. In my mind, I have absolutely no idea how to use it for a practical reason. Most probably, I did find an idea where to use it practically simply as a very weird and very strange clock by itself. So if I want to clock to number from 1 to, I don't know, to 5, and then reset it back to 1 until 5, I will use one chip, and I will link this clock out pin to 5, and it will clock only this 5, and I can have a clock that is waiting 5 passes pretty much. Or if I want a clock that is waiting 10 passes or 10 input clocks, I can use one single like this, with one single row without all this thing. But as an extension, if I want more than 10, I can use this circuit that I'm having here. So beside being a toy circuit, a practical circuit is to use it as a clock in itself, a resettable or a custom clock to count to a specific number of times, and decimal times, not binary times. So it's quite an intuitive clock if you stay in sync of it. It's an interesting idea, but I'm not sure if I will actually use it as a clock. This is a weird clock. I never seen something like this built before, but it is an idea. I think it's a good one. Maybe in the future I will build specifically, actually use it in something. I don't know where and when and how, but that's an idea that I had to put it there for you to get. So next circuit that I want to present is the next level. So this is from 0 to 20, and is using this flip-flop that is having here, and is doing it perfectly. Is counting from 1 to 20, and is absolutely genius circuit. Okay. So it was this circuit here, and then I said, well, I want more. I want 40. This guy is saying that the AND gate can be made with 2 diodes plus 1 resistor, and he is true. But I have quite a lot of AND gates, and I want to get rid of them. This was another point. Let me open my my IC list here. So let me find and the match case, and there it is. Close. So this 4081, I have 21 of them, and 21 pieces. And I never find a use for an AND gate. I mostly use NAND gates, but AND gates, beside using them on testing boards, just for testing the chip itself or some other circuits, and usually it didn't work. I couldn't use it in other circuits. Also, when I catch a circuit with an AND gates in it, I say finally I can use some of those too many ICs that I'm having here, that I'm never using them. I never find a good usage. I never. So that's another good reason for the AND gates. This is a good alternative if you don't have AND gates. I stupidly collected too many of them, and I really don't need so many of them. I want to get rid of them. But if you don't have an AND gate, you can make one AND gate made from diodes. Let me actually show you how it's looking. Actually, I think I posted here something. When A and B are opening these 2 transistors, you will get a plus 6 volts that you have there on the output. That's it. Very, very simple. And this is with transistors, so the voltage is surging through A and B to the ground pretty much. And on the output, you don't get any voltage because it is already surging through these diodes. But you have to stop with a positive on A and B, and you are pretty much stopping the current flowing through A and through B to the ground. And then you will get a positive here. Otherwise, you will get, because you have this resistor here that is limiting the current, you don't get it on the output. You don't get this voltage here on the output. You get only the 0 volts that is through these diodes to the ground. So that's the idea. And I used this circuit, and then after I made this circuit with multiple transistors from this guy here, let me actually show this. Yeah, this is it. All right, and this is it. I'm using my friend circuit for counting, but this is an extension. I can get up to 100. Why? Because I'm using this, instead of that flip-flop, I'm using another 4017, you see, another 17, instead of that flip-flop. Instead of flipping from one output to the second output and then back to the first output and then to second and then to first, second, first, and so on. That's what flip-flop is doing. This is actually switching through all its outputs, 10 outputs. So that's why it's 10 outputs here times 10 LEDs that is having there is equal to 100. I link it to 40 here to 4 outputs, but you can cut this line and put this to ground here, link it to ground there, and you are actually counting to 100 or how many you want, you know. And the thing is that you have to make this little module here with a transistor and a couple of resistors to drive all these 10 LEDs per each branch, you know, for each output. And this is a very good, very interesting circuit. I figured it out relatively quickly. This was not a big deal, but I had others that I couldn't resolve them myself. So this was easy to make, for me at least. Save no. And this guy is coming up with, this is basically the same circuit from Texas Instruments, but he is using, so here is the timer. This is the clock timer with the 555 here. That is clocking this, you can see it actually, from pin 3, from pin 3 is clocking this one, and these other two ones indirectly is clocking them. So that's the clock, and it's using exactly the same Texas Instruments thing, and is limited, very limited on the LEDs that he is using. He's probably using here also 25 LEDs, not the entire 30. As you can see, he left first pin open, not used, and the last one is going back to that chip. And here in the middle is actually using the first and the last pins. So only 8 only 8 outputs are actually used. And I attracted this attention to him as well. I told him, dude, dude. Here it is. Here is the AND gate. Yeah, this is the AND gate that I was using. I remember I put this image somewhere to exemplify it. And this is a friend of mine, a good friend of mine. Look how many likes he's having. 3 likes. So he is actually suggesting with his circuit that he's having here, he remade the other guy circuit with the flip-flop. Here, this is a D-type flip-flop that is having here. Here is the 2 outputs. But the good thing that he is adding here is not through all those transistors, but directly linked to the output, because if you think about it, you only drive one LED at a time. So this output is actually seeing only one LED. It's not seeing all the 40 LEDs or 20 LEDs or 10 LEDs or whatever, how many LEDs you are putting. It's not seeing all of them. It's only seeing only one. If it's older LEDs are 20 milliamps per LED. But if are newer LEDs, you can use you can go into microamps. That's how good they are. They only need a proper voltage to get on them, and after that they are going into microamps land. And following his example here with the flip-flop directly linked to the flip-flop without those transistors, I made this circuit here. Let me show you. I believe this is the one. Yeah, exactly. This is the one. Yeah, this is. So I made his example circuit that he is showing me there here. And I remade it here in my thing that I'm having here. And here, I extended it to 40. And you can extend it further to how many you want, 100 to 200 or whatever. Here I was figuring out how to make it to 40. And I didn't get any help on it. This was a little bit hard to figure it out because of this additional 2 flip-flops. I had to include them here to drive this circuit. Yeah, and here I got down. This I got crazy. Let me see. Where are you? With flip-flops, I believe. Yep, exactly, that's the one. Oh. So 0 to 200. This is a motherfucker. This is a motherfucker, as you can see. Let's see, I don't have anything else. Let me actually show you that is actually working. Yeah, it's working a little bit funny like this. But it is, if you order them correctly, the LEDs, if you order them, you will get a continuous, so it's pair and impair. This is pair A, C, A, and G, you see, and then is B, D, F, and H, you see, and then it's starting again from A. So you see, if you order correctly the LEDs, you will get all the functionality from this. Yeah, no, I resolved this circuit. I resolved it myself as well, and it was very hard. It was quite hard. I tested the shit out of it. Absolutely the shit out of it I tested. So I got into town basically. So you can extend it to 200 LEDs here, the number. Because of this secondary 4017 counter that I'm adding it here. So it depends if you are moving this master reset pin here and to the ground and leave it to count from 0 to 9 or all these 10 outputs, it will go to 10. But here you have 10 and another 10, which is 20, and you have in total 200. All right. So that's the trick. That's let me get into a close-up here how it's looking, just for you to. And this is this 20. It means how many LEDs I'm having on this line, entire line here. I'm having 20, 20, 20, 20 LEDs per each line. Okay. All right. Interesting, huh? Okay, let me close it and not save it. And here I tried. Here I was. So I was full. I was completely okay with chasing from 0 to the maximum, and then getting back to 0. But then I was thinking how to make it reversible. You see, to actually count back. And this was the basic circuit that I found it on internet using. This is actually using only 6 LEDs, not 10 LEDs, and only 4 of them are actually derived through these diodes. And if you follow the logic that you are seeing here, you will understand exactly what is going on and how it is moving back and forward. I believe I have this circuit already made somewhere. And this is it. This is the LED chaser history. So I managed to cascade it up to 200 or to 1000 if you want. If you want to add more 4017s. So this entire thing that you are seeing here, this entire half is only for the chaser, from 0 to the maximum of LEDs that you are putting there. Next is another circuit, is a scanner. Is using the chaser, but one times is going forward and then is getting back. So let me bring up, I believe, this one. Let's see, this is the basic circuit, and as you can see, with only one 4017 is doing this back and forth scanning thing. Again, is running from this clock, which is 10 hertz in my example here. In all my examples, I use this 10 hertz. Is low frequency and is permitting me to see everything. This is version 1 that I tried it with transistors and for more LEDs. This is with 6 LEDs here, but here I'm having let's see, how many? I'm having 10 LEDs. Let's say 5 and 5. So this is an extension from this, and as you can see, it's not using diodes. It's using actually transistors and way more transistors than this simplified, very simplified version that you have here. So if you want to extend it, you have to use transistors and in double rows, and it's getting a little bit more complicated. Plus a flip-flop here, 7474, because this is what I have. But if you have something else, you can use whatever flip-flop you have. Doesn't matter. What it matters is to set it up correctly, to make the settings for it to run correctly. So here I put a mentioning. I couldn't put only one resistor for all transistor bases. So for all this, you see, is having 110 kilo per each base of the transistor. So originally I put one single resistor for every base, and it didn't want to work like that at all. Probably this is a simulator problem, but I believe in reality it will work with one resistor for all 10. But to be sure that everything is correct, you should do it like this, with one resistor per each base of the transistor, or one resistor for two transistors. As you can see, every base, all the bases are linked together to one common base link, and this is switched by this flip-flop, one or the other. It's 5 and 5, pretty much. No, it's 10 and 10. Is 1 times is numbering 10 times until the end here, and then it's flipping. This flip-flop is flipping, and then it's turning back to go in this other direction, and then it's flipping back again, and it's counting forward again through. Is switching this line here for all these bases, is opening all these transistors in the same time, and then when this flip-flop is switching, is opening all this other set of bases of the transistor, but in the same time is closing these, are putting them to 0. So these are off, these top one are off, and only these are open. So that's it. So this was also my circuit that I built by myself, and it took me quite some time until I reached this final design that I'm having here. Okay, so this was version 1 that you can make it from transistors, but here I'm using AND gates because I'm having too many and I want to get rid of them. So instead of the transistors, I kind of find a proper use, finally, a proper use for my AND gates that I'm having, 4081 AND gates. I believe this was, 4081, yes, exactly, AND gate here. So this is the AND gates that I have. So if one chip is having 4 AND gates in it, I can use here 1 chip, 2 chips, 3 and 4, and the last two, and the last two from here, they can be another 1 chip. So it's already 4 plus 1, 5 chips I can use for all these AND gates that I'm having here. Here is a very interesting situation. The diodes are necessary because the output is sourcing, but also is syncing. So I made them sourcing only this way by inserting a diode on the output of this AND gate. So sourcing and syncing, you can. I had some errors because this gate is connected. This output is connected pretty much to this other output gate. But when this is sourcing, meaning that, let me actually draw it for you. So here I'm having positive like this. Positive, and I'm sourcing from this output. Let me change the color here. But here, this is syncing the current, and is negative here. And the current, and let me draw it with red, and the current is going from here, is connected. You can see it clearly. It is connected there. And instead of going through the LED down, is actually syncing through the chip to the negative rail there. You see? So that's the syncing and the sourcing meaning. But without the diodes, without these diodes. But by adding the diodes, is basically stopping syncing into the chip, through the chip, and syncing through the LED to the ground. So this is clear as mud. So that's a very interesting usage of AND gates and their outputs in the same time. So this was a little bit of problem, and this is another thing that I made by myself. I didn't get any help from anybody. It was a very good exercise, very good, and I learned a lot about specifically about AND gates and what you can use them to replace transistors, basically. So if you want to replace some transistors, you can use some AND gates. It's a very interesting idea using this AND gates instead of transistors. It's very interesting, and I really like it. And also, I'm really glad that I find it. And again, it was a very good lesson. Okay, this is the scanner number 2, also for 10 LEDs. So this is a direct replacement for the first version. So this will work absolutely fine, like the other version. As you can see, I'm playing it now. It's running absolutely okay. All right, so I'm stopping it. Let me follow the history that I'm having here on this forum. Here I tried, like I said, with transistors here, and here is a replacement, but it's exactly the same circuit, but with AND gates instead of transistors. Whatever you think is better for you to use. Next, I wanted what I want. Next challenge. Here, next challenge. Sync for a LED scanner containing 20 LEDs, driving it using logic gates and flip-flops. I'm already on it for probably 5 hours, and I still didn't figure it out. It's very, very hard. And it was. And I couldn't solve it. I couldn't solve this problem. So pretty much the next challenge was from this 10 LEDs that I'm having here to extend it, to cascade it, instead of this 10, to cascade it further to whatever number you want. This time, I wanted to cascade it to 20. Back and forth. Remember, this is not chasing LEDs. This is a scanner which is counting left, then turning back to the right, and then turning back to the left, and so on, is scanning back and forth. So this is a completely different beast and completely different circuit from the chaser, which is extremely simple to make. And this was, I stayed probably one day and a half, and I poured my brains out, and I couldn't solve it. I really couldn't solve it. So pretty much what I did a lot of homework. I prepared the circuit before I posted it here, before getting the correct answer. So I formulated the problem correctly. This is here. This is the final one. So until finding the actual circuit that is the logic block, this logic block, I couldn't figure it out me by myself. I couldn't figure it out. But I managed to formulate the problem correctly, and I changed all these lines that you are seeing here a couple of times for these top ones, for these vertical ones, for all of them, for partial of them. I changed them numerous times, and then I revert back to the original how it was, because the original was working. And I was thinking because I was getting all the time, I was getting a ton of errors. It was not going circling forward and backwards. It was jumping around. It was not switching at the correct time. I was having a ton of problems, and I couldn't figure out this logic block that I'm having here, that is now functioning okay, that my friends find it for me, but I couldn't find it by myself. But at least I formulated the problem. So like I said, I changed a lot of these rails and these ones here, and then I revert back to the original how it was. Let me show you, like here. You see, probably it's like there. Huh? No, it's not like there. Well, no, not really like there. Not exactly like, but it's kind of the same. Going up and then going down. So pretty much like that, going down then going up. That's the logic. Like a sine. Like a sine wave is like that. Only that is inverse like that. But because I changed it many times, I changed these connections here in the idea, in the hope that it was a logic wire problem, wiring problem, and it wasn't from that. And when I realized after many 1 day or so, or 1 day and a half of struggling, I was giving up on this project. Actually, I was on that point of giving up because I tried so many things and I couldn't figure it out why it's not working and why I cannot get a functional solution from it. And then this red scribble is the logic that I needed here, and I needed this sequence. So let me show you here. So this is first flip-flop, this is the second flip-flop, and I named them as A and B. And all I need for this A and B is the input clock. All that I need is this input clock. And the tests that I did to figure out this sequence that you are seeing here, this red A0, B0, but I'm referring to the inputs of them, not the outputs. But also, I'm having it here, as you can see. Also, this positive, not inverted output is actually responding exactly to this sequence. When I'm clocking it here, I'm getting exactly on this output, exactly this sequence. So this guy here and this guy here that is representing the this positive output or non-inverted output is responding to this sequence, but I find it later, this analogy between. But what I was originally referring here, I was referring to the clock that is getting it into the flip-flop. So A0, B0, it means to stay at ground, and A1, it means 5 volts. And B0, it means 0 volts, okay? And here is 0 volts on A and B. So as you can see here on this line is not connected to anything. Because this will be 1 here, it will be high, but by not connecting it to anything, it will stay low because the other circuit that is here, that is keeping it to 0 volts, is keeping it low. And then I'm having this line, the second line here, the second output, that is making this input here for the clock 1, and then a 0, and then which means 5 volts and 0 volts, and then the next is 5 volts, 5 volts, so 5 volts here, 5 volts here, and then 0 and 1, and 0 and B1, so 0 volts here, and 5 volts here, and then cycle back and do it again. But and here is my explanation what all this 0 and B0 means, where 0 equal no clock pulse or no change on the clock pin, I forget to mention it, and 1 it means one pulse clock, as 0, 1, 0, starting and ending with 0 and only once. So this is a one single clock pulse that I have to do when I'm saying I'm doing this A1. The A1, it means one pulse clock. So it's not staying on 5 volts, but it's doing 0, 1, 0, and let me actually show it. So it's doing exactly what I'm showing you here. So for so this A1, B1, so here will be 0 volts like this, 0 volts, okay, on B. So we are here, and A1, it will be 0 volts, one clock pulse like this, 5 volts, and 0 volts again, and we'll continue to stay at 0 volts indefinitely until it will reach again, until it will finish all this loop, and it will go back to this pin, and it will create another pulse. How fast this pulse should be is how it shouldn't be faster than the clock signal that is having there, that is being able to respond, you know, to sense it. So I was in my other experiments that I did, I have a ton of experimentation that I did here, and I did it with, so this was the basic LED scanner, blah blah. And I did a lot of stuff. I was doing it in binary. I was trying to make it in binary. I was doing a lot of flip-flops combinations, and then with AND gates and stuff like that, and with transistors. Actually, I believe this worked with the transistor. I managed to figure out that it is a clock pulse and is not a single pulse that is remaining on high all the time with this schematic circuit that I'm having here. This is how I managed to understand what I need. And originally what I tested with, do you see this button here? If I'm clicking it, so I'm clicking it, and when I'm retracting my mouse and I'm not clicking it again, it's starting with 0, it's creating 1, and it's getting back on 0 after I finish clicking. So this is a pulse creating this clicking. So this was the button that I was using to clock these pins from this flip-flop. So I was using that button like click, and I was pulsing it once, and I was staying and with patience, and I was following what is going on here if it's counting correctly. And this is how I managed to figure out this entire sequence that I'm having here. Let's make it by the book. First of all, you can see here in the titles here, this A flip-flop is changing the negative rails, and this B flip-flop is for left and right. Okay, and what this means very generally, the left and right is this rail here. This is one rail, and this is another rail here that are going only for this left and right flip-flop. That this flip-flop is commanding these two rails, okay? And this flip-flop is commanding this rail here or this rail here when one is positive and the other is negative. But in reality, this will be positive and this negative, and they will flip. This one will be positive here, and this one will be negative. You will see in a second what I mean. But pretty much these two flip-flops, what they are commanding, each of them. Okay, the rails on the bottom are for flip-flop, this A flip-flop, and this B flip-flop commanding this and this rails, those two. That's it. Okay, this is the general introduction. Now to get into the details and to actually follow the steps. So in the beginning is A0, B0, and let's actually draw it. So so this rail will be positive here, and this will be negative here. So this is for this flip-flop A, which is changing the negative rails between these two groups. And now the left and right flip-flop is activating only this line. Only this line here is activating it. Actually, it's positive here, is a red, and this is negative and a blue. But I'm using the green color to actually differentiate and be a bit more clear this way, and it will be more clear this way. But for you to know that both flip-flops are using the same colors for negative and positive, red and blue, you know. Now it is activating this line. Right now we are at this line A0, B0, and this LED here is the starting LED, is starting this to work, is waiting for this flip-flop to get to the last output. So basically to this LED, this to reach this LED here. When it's reaching this LED here and when it's resetting, actually when it's getting to the first one, to begin the first one, is resetting this last one, and also is resetting this here, and this is switching, and when it's switching, it's creating the second line of code that we are having here. So right now we are here at this second line of code at this point, and this means A1 and B0. So B0, this is B here with the green, and it's not doing anything, so it's remaining unchanged. Only A is changing. So now, conform to this diagram, is creating this line negative, and it's flipping the rails. It's literally flipping the rails. So before flipping, only this was activating, but now only this is activating. Even in the same time, they are both, these two groups are in the same time powered from this activated from this top line, from this flip-flop that I'm having here. Okay, so this is the group that is activating now, and remember when that changed to the first from here, it changed to get to the first one. Immediately these flip-flops they get activated, and instead of this LED to get on, because the rails are switched, now this LED is on. Okay, and then it's continuing to count. Is letting that this counter here is counting 1, 2, 3, 4, 10. So it's reaching this point here, and when it's reaching that point, the last bit that is having is switching, is creating this clock out pin probably, and it is switching to 1 again. But when it's switching to 1, is actually activating this counter as well, and it's switching to the third line. And now we are on the third line of code here, when it must be A1 and B1. But as you can see, this A1 remains the same. So this first flip-flop doesn't change now. The rails remains the same. They don't flip. But this guy, B0, this guy here, this is changing from 0 to 1. This is the same. This is changing. And so this is the guy that is changing right now. Let me deactivate this line that I'm having here. So this is my desactivation color. And I'm activating this. So now is activating this side here. Remember, the LED is here. And when it's in the moment it is activated this side, you see, you can follow this guy is activated as well. And this LED remains on. And then the counting is starting again. This 4017, this counter is starting again from 0, like usual, but now is inverted because this stuff. So now it's counting. Now it's counting in this direction. If previously was counting like this, now it's getting back. So now when it's finishing from here to count, this LED is activated here. It's finishing counting. Is again is this counter CO counter output will flip once again, and it will clock this counter again, and this will change to the fourth line of code. So now this rails, this B flip-flop remains the same, so nothing is changing here, is remaining the same, but only the rails now are changing. You see here the negative rail flip-flop that is responsible. So now what we are having there on the bottom becomes like this: pack, pack, and pack, and this is negative here. Okay, and now when it's starting to 1, this is the one here, and then the counter is moving all its outputs to the last one, and is reaching this LED here, and then the cycle is starting again. Is starting again from 0, and as you can see, everything is and when it's starting again from 0, actually what you cannot actually see it from the first spot is that this fourth line and this first line, this B1 is changing into B0. So A remains the same, the rails remains the same, but now it's changing the activation there. You see, I'm disabling this rail, and I'm enabling back this, and right now is exactly as we started from the beginning. Now we are at exactly at this point in the beginning here. So you see the flip-flopping and how I had to think about all these things, to account for everything. It's a bit complicated, but I'm glad. I hope it now is a little bit more simpler to visualize the mechanism that is happening here and how I actually obtain this sequence that I'm having there. So now I hope this is more logical right now at this point. All right. So getting back to here, this was the question after I tried many stuff, many things. And here I'm presenting what I was trying to do, and I did with a Schmidt trigger. Here it is actually. Yeah, it's exactly this guy here, what I'm having there in the picture. But as you can see, I have many other tryings and problems, and I'm trying to resolve this issue. But I probably, what I did here, this was way too fast for that clock to respond, to actually understand that this is creating a pulse here. This is creating a pulse, but it's doing it at an enormous fast speed, very fast. So it's faster than the clock pin that can read. So that clock is very slow and is like an old, is barely seeing stuff. But this moving very fast, it was, yeah, something had happened there. It's like a blip for him. And what he is seeing, that the clock pin here, the clock pin is seeing like a tiny little blip, is starting to create a blip there, but he is ignoring it completely. So sometimes I was getting a response, sometimes I was not getting a response from this circuitry that I was using. So this is how I deduced. This is most probably is doing it way more faster than the clock is reading that I'm having there. And I couldn't resolve this problem at all. That's it. I couldn't resolve it by myself. And here I was showing my tests, and then my friend here is coming with he edited finally the correct version, because I tested it and I told him, yeah, it is correct for me as well. And indeed, this is the correct version that I'm having here, that he is presenting. He actually presented 2 or 3 versions of this circuit, but I believe he changed only the wires on these OR gates here, the way they were wired there. And that's it. And that was the salvaging circuit. This was the logic block. And for the life of me, I couldn't think of it. And I asked him, how did you think of adding this OR gate? And let me get to it, actually, getting on page 3 here. And I give myself a response to what he might have did. Here it is. So I believe probably how he get to this particular circuit to make it work. Yeah, originally he was having 2 OR gates there, but I simplified with 1 single wire, because the other OR gates was having 2 of them, 2 inputs linked together. So I simplified with only 1 link. And he replied to me, well, that is good as a buffer, but remember this chip is also buffering its output, so it's really not needed for that extra buffer there. It should be okay. But going back, how the hell did he came with this circuit? I have absolutely no idea. And I believe that he actually followed this diagram. He looked on all these outputs of the OR gates, and also on the inputs what it is needed, and pretty smart for the OR gate usage. When the inputs are zero here, practically holding the flip-flop clock to 0 all the time. So here it is. So this clock pin is keeping it to 0 all the time when these 2 inputs are 0 okay. Until 4017 changes its output. So this first chip is when this is changing its outputs, is creating a 1 and a 0 somewhere. Probably you chased a gate that holds a 0 input to a 0 output, and that's how you decided on OR gate to use. I'm still mystified. How did he get to this circuit, and how is actually functioning? He never responded to me because he probably doesn't know how to respond for this weird or stupid question that I'm having. But it's very important to me to know about this stuff, because I'm trying to learn this shit. But yeah, very interesting, and I couldn't resolve it by myself. So it's good to have a good friend that is out there, that is helping you with other versions of the circuit, with other possibilities. And if it's smarter than you, way more better, because he will actually make it work, for you. So let me show you how this is working right now. So this is, yeah. Okay, you can follow here. I can zoom in, actually. You can see here it is. The functionality. You can see it's stopping a little bit because the simulator is trying to think ahead, probably, and it's freezing a little bit from time to time, like there and here. But it is doing the correct sequence right now, absolutely perfectly and continuously. Because one other very important error that I was getting myself when I was building my logic circuit, one time was getting here, and then it was getting back, and when it was reaching this last one, it was starting from other place, and it was switching erroneously. So the first round it was doing it correctly, but then after that it was getting into error mode, and this actually made me believe it was I was doing good, while it was in reality it was a bad circuit that I was having there. And then later I was realizing this little detail. So the important thing here, so I stop it right now. The important thing here is that this is functional, but it's very complicated. It's quite complicated circuitry only to drive back and forth over this lens. Now, this is it for this movie, which is a bit too long, unfortunately, and I'm sorry for that, but it was a very interesting and long project. And unfortunately, like I said already, this is more like an exercise for logic circuits to get more into depth with them, to get to know them a little bit better, especially the flip-flops. And it is, for a practical point of view, it is a toy circuit, what I'm having here. I am not sure if I can actually use this circuit in a serious practical circuit. And I cannot find right now a practical reason for it to use it. But maybe in the future, maybe for someone that will need this kind of functionality, you can see that it's a little bit more complicated to build it, but you will get this functionality in the end. Even if it's complicated as it is, you will get it. You'll get this functionality. And that's all that is important, you know. And yes, and with this, I will close this movie, and I will say to you goodbye. And I hope you liked my entire presentation that I'm having here. And with or without my friends' help, it doesn't matter. All that it matters are the results. And there are results, and I'm very, very happy that I managed to push it so far, as crazy as it looks from the circuit perspective, on some models that I'm having here, but it works, and I'm very, very, very happy that I managed to make everything that I put in my head to make. It worked, and it's fantastic. And I'm thanking to my friends, to all my friends, for their invaluable help they give, and very, very cool project. I really like it, and it was fun. Yeah, it was fun. Okay, thank you very much for watching. Thank you very much for listening. And I hope you learned something. You learned how complicated stuff is, how to make it work, and that it doesn't matter how complicated it gets. All that it matters is to have good friends and to make it work. That's all that matters. All right, thank you very much. Bye-bye from your favorite artist electronics, Mr. Q12 here. Bye-bye.